So which dotted curve is better using correlation? This one, right? Because it does the exact same thing, so to say. And this does the exact opposite. So like I tried to make the opposite, right? So it goes up when this goes down. But if I look at it, and this is like a range from 0 to 1, and like this might be actually only like 0.8 here. So it's not that far off, but it just doesn't get these curves.
It doesn't follow the pattern.
Right. But this follows the pattern, but you can be completely off. Like this is 0.2 down here, right? So you're actually, and this would be like, the correlation would be 1, right? And here the correlation is 0, or like very small. And but you would almost argue that maybe this is actually better than
Because
this
the
one.
ups cancel out.
Yeah. And so what they're trying to do is kind of combine both the trajectory as well as like the distance of each point, or like the average. In this case, this is kind of like the average of where the signal lives in. And this can be more, you can make this more precise here as well. If you, for example, have here like a sum and you subtract each single dot from each other, and actually compute the mean distance between the two signals instead of like taking the mean and mean.
Because
and
you have two
subtracting
lines,
mean.
right?
Yeah, because so what it doesn't get at is like, I mean.
So for this one it says 0.3, for the other one it says 0.7, and that's it. So you have a scalar, and the end it says 0.5, and you have no idea.
And this line as well as this line have about the same mean, right? So you don't get this this information either. Okay, so that's kind of like what they're trying to do here. And anecdotally, this happened because I told them in 2012 that correlation alone is idiotic. And they're like, oh, we're looking for a new measure. That was we organized a conference here, 2012, called the International Conference on Multimodal Interaction, and back then they already had this challenge with a different data set, and they only used correlation in it. And I said that's like it's not working, and a friend of mine actually won the challenge at some point with with a little trick, and when they handed him the certificate that he won the challenge, they said like, congratulations for breaking the challenge. So what happened is the following. So he didn't really care. So the target here is again the same thing. You try to predict emotion or affect based off of like a video that you're seeing, right? And so he didn't use any of the audio data or the video data at all. All he did is like, I take the amount of time that has elapsed since the start of the video and take the log of that time. So log of t was the function that he used to predict the emotion. So this is t. How does that look like? Well, log of t looks something like this, right? And then it saturates at some point, but it goes up and up and up. And he knew that, or he did that because the evaluation criterion was just correlation, okay? And he plotted every single emotion trajectory of every single video onto like one plot, and all of them, for whatever reason, looked like this, and then they did something here, right? So this was all how they all looked like.
Okay.
And that was because the annotation tool made everybody start annotating with a 0. It's like, no, it's not a 0, it's go up, right? And so this part here is responsible for most of the variance of all the annotation signals, right at the beginning. And if you get that correct with log of t, you do, then you actually cover most of the variance of these signals, and your evaluation or your prediction correlates very highly because it captures also that moment of high correlation, right? And so, or like high variance in the same way. And all of that happens up here is all kind of random noise. So that's how he broke the competition. So what this should kind of tell you is it is always important to use the right metric. Concordance, correlation versus correlation. So that's some, like, I guess a lesson learned that we should all kind of consider. Okay, so what else happened in this paper? Well, they got really good results, didn't they? So they basically increased this metric by double, right? Like they almost from 3.382 to 686. That's pretty much double the output, and that's pretty strong actually. But then you see this here, like that, not that great, right? And like here, I mean, this is on your validation set where you optimize for this. So this is still pretty bad. Let's look at what these numbers are. So this is arousal. What does that mean? That you're really good at predicting arousal. So arousal and valence are the two like orthogonal dimensions in this emotional space that they are looking for. So you have low arousal to high arousal, which basically gives you low energy, little change in the behavior, to very high energy, much change in the behavior, higher variance. Okay, and then on the valence side you have positive versus negative valence. Negative valence, possibly you would frown more, like you show your teeth, you might use negative language, say swear words and stuff like that. On the positive side, you're like happy and excited, and like there are positive words, you smile more. You might also smile on the negative side if you're like through these kind of like display rules in human culture, and in our culture, like it's not as expected or acceptable to express like full-on anger. You might just smile at somebody. It's like, yeah, like I'm gonna get you, or something like that. So it seems to be.
So is this a set that is dialogue, or it's a reading, or how does a set look like? Because that also means that they are good in figuring out where the one speaker ends and the other speaker starts, because it will be triggered by engagement. Arousal will be triggered by engagement.
Right. So the Reikola data set is monadic, so to say, like it's a single person talking to a computer screen. I don't think that they actually have these kind of like switches.
Right, but am I wrong? Because arousal, predicting arousal will be, here I start, and whoa, you predicted, great.
Right.
No, right? Yes.
Uh,
and if you listen to a dialogue,
yeah, so
you see
right.
that the intonation goes up, you know that the other one is kicking in, and you go like, okay, I got it.
Right, but so in this case, arousal, I think, because it's only audio alone, in this case, arousal is really related to loudness in the signal. And that's also one of the reasons why these features of loudness were predicted so well. We're going to get to that in a second.
So are they reading the same text?
No, I think it's like free speech responses, but it's in French, so I don't really know. And so yeah, so they're kind of getting pretty good results here, okay? I would say it's not bad for arousal, but then it's really bad for valence, okay? And so what the interesting part here is, and that's also like one of the things that I always, like when I see their papers, I always respond in a review, like you have to compare this to humans, like human performance. What do humans do, right? And like in every single other data set where humans rate this stuff, basically the agreement between humans, so you have, like, let's say you have one video and you have 3 or 4 humans rate the same video, okay? Pretty much, like if you remove one human from the group and you try to predict the mean or the average of 3 humans' opinions with that last 4th human, then you get pretty much the opposite, where humans don't agree on arousal at all. Most of the time they don't really, and they always completely agree on valence. Right? So because we listen to the content, we listen to...
So much more important to us to know that somebody is angry.
Exactly. Then
Yeah.
how angry? Like
Yeah, exactly.
It's like, is it 0.4 angry or is it 0.5 angry?
Yeah.
It's
Am I
not
going to be beaten now?
exactly. It's not a concept that we have an understanding of. Okay. So.
So like the Honda commercials, no.
Right.
Which one?
The Honda commercials, you know, they're, oh yeah, you won tickets, or you know, oh no, you did, oh, you know, another person's like, I did, but the other person, no, I didn't. So all these different people have different.
Right. And so this is quite interesting, I think, and I feel always like if you do like these subjective examples, and like there should be a baseline that always says, okay, this is how humans do in this task, okay. So I would like to see that more, okay? What else is surprising here? We only looked at the B part of this table and evaluation thing. What about the A part, the mean squared error objective? I have no idea why no reviewer like picked up on that, and I didn't review this paper. But the mean squared error of the proposed thing here is abysmal in comparison to all others. That's an error measure where you want to be as like small as possible, right? So these values here are huge.
Oh, yeah.
And they're actually the worst of them all in both. And I'm like, why? What is happening? And like, in this case, I really don't know. It might be because these guys here predict like the flat lines and like fit the mean value pretty well, but I'm not sure. I'm not 100% sure in this case. But like, yeah, this is so interesting. And it's, I mean, like it's mean squared error. It's not like good is high, right? So it could be that they, in fact, actually completely overfit on their concordance correlation coefficient objective rather than like if they, and so they train on a different objective and evaluate it on another objective, which I think is interesting to see. So yeah, like I'm not sure what's going on here exactly, but.
So overall, they got a.
Oh wait, we optimized the models with respect to mean squared error, whereas in B with respect. That's even worse now. So they optimized it for mean square error and got even. Okay, that.
But overall, what did they achieve? I mean, they somewhat recognize arousal better in raw signal than definitely than humans do, but they don't understand valence, so how are they really understanding emotion? I mean, what's the objective of a paper is to feed the raw signal and figure out if they're happy.
Right. So,
And I don't,
and I know a couple of people that work in like startups that want to try to do this, and they say basically, okay, so what we get here, the performance that we have in these kind of approaches is completely useless. Like it doesn't help us at all. Like it's not giving us performance that we can actually use in a day-to-day or in a real application that people use. And like an arousal detector, if you're that good at arousal, I just want to know like how good is like just energy of the signal as well, right? It's like that might be pretty close as well. Anyways, so this is kind of like, it's always important to, I guess, like to understand really what like the measures are and what's really going on in either case. Okay? So I think that's very interesting. Then this result I think is kind of nice. It's interesting in the sense that they try to basically see if some of the activations in the neural network are correlated with audio features or speech features. And in this case, there is like two features that are energy based, so energy and loudness. Does anybody know what the difference between energy and loudness is?
no, I don't remember, because we got it from
But
the,
like a decibel.
is it
loudness,
coherent?
Energy, decibels.
So both could be measured in decibel.
Alright.
But so energy is a physical or like physics-based measure of loudness or of like the intensity of a signal, and loudness is a perceptual measure where you actually consider the human as the perceiving agent of this signal.
So it's in
And
hell.
Yes, and so what is it actually called? Phone, I think. So mel frequencies are used to, or like the mel frequency domain is used to measure it. But like so what that basically means is like humans hear better in certain frequency ranges and are more sensitive to signals in certain frequency ranges, and are less sensitive to others. So if like all the energy of the signal is in very high frequencies, like 20,000 hertz, we don't really perceive it as loud because we don't really hear that well in 20,000 hertz.
But dogs do. And
But
that's
dogs
why.
do.
Then it,
Oh!
it's like
Yeah,
it blows them away.
Right. So these dog whistles are really loud for dogs, and like and are not so loud for us. Right. So that's the difference between that and then fundamental frequency is basically the base frequency of a signal, and like how the vocal folds are vibrating. And so yeah, these are the cell activations. So they're trying to like investigate like what part of the network learns kind of like what feature, or is it related to a certain feature. So and they find this kind of interesting result. And again, all of these signals here are very strongly correlated with arousal.
So is there a difference between like the man and a woman's voice, the way they're, because a man has a stronger.
There's a difference for multiple reasons. So first of all, typically men are taller and have a larger vocal tract, so the frequencies that we observe for men are always lower, or most of the time lower. And there are some other social things about like men sometimes tend to be like louder and like they want their voice to be heard more, and
Okay.
are more
Alpha,
annoying.
the alpha male, yeah, I understand that,
I
okay.
think didn't they do something in the beginning to get this, to mean them to zero?
Right.
Just to compensate for that, so that we don't know if
Yeah.
these are.
I actually didn't see that, but
I think it's in the beginning
Oh,
of
the-
2025.
but I'm pretty sure they did. Scaling factor, scaling using the ratio of standard deviation of close. What? No. Median filtering with the side of window range, centering.
It's in, we segmented row wafers.
Where is it?
I think it's 2.1, under input. You can process the time sequences to have zero mean and mean at variance to account for variation.
Okay, got it. Okay, yeah. Yeah, that's fine. That's like what you would do. There, you need to be careful, like with respect to what you're doing it. Like if you're taking the entire data set, you wanna sometimes you wanna normalize with respect to like only one speaker. Sometimes you wanna normalize with respect to every speaker. And if you take like mean and variance, sometimes you need to make sure that you're actually just taking for the training set and not the test set. So there are a couple of things in there that need to be considered. But then, so how big is that data set, by the way?
15, 15, and 15.
So it's 46 French-speaking participants with 5 minutes for each. So you have, what is this, 16 times 5, 15 times 5, and 15 times 5. So you train on 16 times 5 minutes of data. It's not
Tiny.
much, right? This is very tiny. How big is their network?
2 layers, 2 convolutional layers of LSTM, and then I forgot what else.
That's like 2, yeah, so not, you would think it's not that big, right? But, where was it? It has 1.5 million parameters.
Well, isn't that given that you're overfit?
Let's calculate.
Didn't you tell us that if you have, if you
5 times 16
go,
is 80, so they train on 80 minutes times 16,000.
whoa,
Oh, it's interesting.
1.2.
million data points? No,
They have 1.2, oh this is minutes, sorry, times 16. So they have,
Oh, 60, that makes.
they have 50 data points for each input data point. So I just
Yep.
don't understand this anymore. So yeah, like and they actually like it feels like so the raw waveform comes in at 16 kilohertz, okay, but they're downsampling it to like 8 kilohertz and in here and stuff like that. It's like I just like I don't think it's really that important, like that necessary to have these ginormous networks for these kind of tasks. And yeah. I don't know, did they do like a validation of like the size of the network? I don't think they did. Yeah, and so they needed to use dropout again at a rate of 50% to minimize overfitting. I think they could have also used a smaller network.
But what is really the gain? Gain is now you're somewhat better in getting valence that you can probably get from just the support vector machine and energy.
No,
You will
valence,
you will be
like not
valence-
necessarily.
Oh, I'm sorry,
like,
not valence,
yeah.
arousal.
Yeah.
Arousal. So arousal is not that difficult to get. CD and I were able to get arousal when we were looking into angry versus happy. But valence is very hard to get.
Right, and that's also
And they're
what
poor.
what the autoencoders that I showed you guys in one of the lectures also have the same problem, that they get really well in separating arousal and not that great at separating valence. So valence is really hard to do.
And this is why you need multimodal, you need face. And
Yeah.
then it kicks in and suddenly you're
And it's traditionally easier to get valence from facial expressions than from the audio. That's also sometimes important. Well, yeah. That's kind of like this paper. So I think a lot of interesting things happening here. It is certainly like the first end-to-end emotional cognition neural network. I think it is a bit large for the data that it had to train on and to validate on. I think they could have like talked a bit more about like what this actually means. Like, is it actionable? Can we actually do something important with this? Like, what is the difference, arousal and valence? Like, traditionally, valence is a lot harder to recognize through audio, but the interesting aspect to it, I think, is that humans are so much better at it than when you ask them about arousal. So, yeah, many different, many interesting questions here, and like open problems, and I think it's a good start, but I wouldn't yet answer this question with yes. There's still some value in feature extraction, just use different features. Yeah. Are there any other questions or comments?
Can I ask a question from from Monday?
Mm-hmm.
Why is ReLU better than Tangency Hyperbolicus?
Okay.
I'm sorry, I was trying to find that answer and I couldn't
Yeah.
figure it out. And I see that that's a big improvement. I don't understand why.
So there is a couple of reasons for that, and so in the paper they say that you're basically using ReLU, which is this, right? So that's like a 0 here, or a threshold, and then like these are negative numbers here, and these are positive. So it's the max between 0 and x, right?
Mm-hmm.
And so first of all, it's very fast to compute.
Mm-hmm.
And then that's the easy one. But then you have the Tangency Hyperbolicus, 0 is here, so you have -1 here, and you have +1 there, and so that's 10H. And then we have a network with like many layers, right? Then we have a learning rate. We always have a learning rate. Like that's our eta is a learning rate. What's the learning rate usually?
0.6.
The learning? No, I mean, well, I guess what did they use? I think they called it epsilon. Anyway, so the learning rate is usually like 0.001 or 5 or something like that, right? Okay, and then so in backpropagation you compute an error here, and you backpropagate it here, 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 here. Okay, and so you have a learning rate in here that is multiplied with the delta of your loss and the delta for each weight, right? And at this point here, you kind of have like one term here because all the others are not important. But then here you have this and like the weight, so the weight's here and the weight's here, and you so these weights are usually small. So like the further you go back, the more times you're multiplying small numbers, right? So at this point you have like small numbers to the power of 5, right? So that's tiny numbers, okay? So that's another issue. That's kind of like this vanishing gradient problem, all right? And so what does this now look like? If you, and these W's are always dependent on the activation functions that we have, right? So, and then that means we need to get the derivative of these activation functions too, right? So what is the derivative of this? This here.
It's the.
So like if we have this
it's
here, so this is 0, right? So that there's 0 here, and then 0 here. So what does this look like? So it's like
It's gonna be
small, goes up, and wait. Right?
Yeah.
So it's tiny.
Yeah.
It's tiny. It's somewhat useful here, and like it might be 1 or something at the maximum, right? But here, what is the?
1.
It's 0 and 1.
Yeah.
So here, if you use tangents and parabolicus in each of these activation functions, you're probably multiplying a small value 5 times again, right? So that's why your gradient goes away.
down.
But with the ReLUs, every single time you just multiply with a 1.
I see.
So you
So
keep
you're
it the
not
same.
losing the gradient, and you're actually going deeper into propagation, which means you're training your network better.
Yeah. So, and these tangents and parabolicus, like these are the regions of saturation.
Okay,
Okay.
got it. Thank you.
Yeah. No, I have to leave.
Okay. So we see you Monday for the exam.
Not this Monday though.
Next Monday.
Oh, wow. My life suddenly
been here by
turned to even
yourself.
better.
yourself.
Sorry, what?
You'd have been here by yourself, you would now, but now you know. You're here, you're good. You're
I
good.
cannot believe this. So, oh my God, I survived this semester. Whoa.